Okay, great. Okay, so I'm talking about this. Okay, so I care about my symplectic manifold that I care about is R4 with the standard symplectic form. And suppose you take any Lagrangian surface, take whatever you want, and suppose it intersects these parallel hypersurfaces, so copies of R3 that's drawn here transversely, okay? Then we get some Lagrangian cobordism from this lower slice LA to the upper slice LB, where A and B are the fourth coordinate. Okay, so I'm going to always be thinking of the y2 coordinate as like time. Yeah. Okay, so we get a Lagrangian cobordism, and a sort of general question you can ask is, given two candidates for slices, can we get such a Lagrangian cobordism? Note that I use the words from and to because Lagrangian cobordisms really have a direction, and we'll see that in this talk. Like if you can't turn things around usually. Yeah. Okay, so this is a question, and the answer is sometimes, as usual, but we don't need the information of these. So these things are like links, and we don't need the entire information of the links. We can actually do things with much less information. So I'll tell you what that less information is. The information I'm going to talk about is the enriched knot diagrams. Okay. So what is an enriched knot diagram? It's a usual knot diagram if you've done any knot theory, spoken to some topologists. So there's a immersed curve in R2. I've drawn them like this just to keep track of things. And there are some signs. So the signs are like positive and negative. It's slightly different from the topologist signs. For me, the signs come at each corner. So at each corner, if I'm like walking along the along my curve, if I'm going like this and I jump up, it's a negative sign. And if I'm going like this and I jump down, it's a positive sign. So if you've looked at sort of Chekhanov's DGA, it's the same signs. Okay, but the special thing here are the areas. So we get a bunch of these sectors that the immersed curve sort of cuts out, and we want to keep track of these areas. That's the information we want. So when I say enriched knot diagram, it comes with a usual knot diagram plus some areas. Yeah. You have a question? No, okay. Okay, and given any sort of the candidates we were talking about in the last page, any knot or link in R3, we have a projection to R2, which is sort of the standard projection. And we also have a framing, that's the, you'd call it the Z coordinate, but for me, it's the X2 direction. Yeah, and that gives me the signs, like the X2 direction tells me whether I'm jumping up or down. And the areas are the actual areas with the standard metric on R2. Yeah. So given any of these, we get an enriched knot diagram. Okay. And some technical term, I call an enriched knot diagram exact if the total area, so I could be going like this, then I take positive. When I go in the other direction, I would take negative. So there's a signed area. Or you could think of the integral of just x dy along this curve. If it's 0, I call it exact. Otherwise, it's not. So in this picture, these trefoils are not exact. Yeah. But if to the trefoil I add a giant loop on this side, I can make it exact. But we'll be considering both of these. And those things on top are exact. Okay. Sort of a crucial point is that if you have a diagram, you don't get a unique knot. So you have a projection of your knot, right? And I haven't specified any heights. except the sort of relative heights of the crossings have to be something, but they could be huge, they could be small. We don't know it. So there's not, it's not a unique knot, but that's fine. In fact, I'm going to even cut down even more information. So if I have two diagrams and a diffeomorphism of R2, compactly supported, taking one of the diagrams to the other while preserving the crossings and the area. So it can like squish it or pull it, but the crossings stay the same. Okay, so it could be a nice round thing like that or a very thin one. Those are going to be equivalent. And all of the theory we're sort of developing passes through these equivalence classes. So it doesn't matter that there's no unique knot. Okay, so questions? Yeah.
So, I mean, is the knot you get like unique up to some kind of natural isotopy of symplectic? I feel like
so this is it. So if you have something that's like an isotopy of R2, like you take the projections and you have an isotopy going from one to the other, like a Hamiltonian isotopy or something, then you get this also. Okay. Yeah, so the harder part is from going from here to the Hamiltonian isotopy, and it works because R2 is simply connected and stuff.
Okay, so this is like the same as them being kind of Hamiltonian isotopic?
Yeah, like the projections being Hamiltonian isotopic, and the heights only matter up to the signs. Like you can't change the crossings. Okay. Okay, so now we have this, and we want to like translate this existence of Lagrangian cobordisms to something between the diagrams. And I'm going to say a diagram D1 undercuts a diagram D2, so it's sitting under something like this. If there exists, I'll tell you what that means, a relatively exact Lagrangian cobordism says that the bottom boundaries diagram is D1 and the top boundaries diagram is D2. Yeah, sort of natural idea. And the relatively exact is a slight weakening of exactness or weakly exact. So for, okay, if you have such a Lagrangian cobordism, both the top and the bottom diagrams have to bound the same area. You can do some Stokes theorem, it works. Okay, so like I say the area of a diagram is that integral, small a, and then a Lagrangian is relatively exact if, a Lagrangian cobordism is relatively exact if the image of the symplectic form on the relative pi2 is always a multiple of that area. It's sort of technical. If you don't see it, it's fine. This will come up later when we want to like prevent bubbling, because I'm going to bring holomorphic curves. Okay, but it's just a like sort of necessary weakening of exactness that lets me treat things like trefoil knots. Okay. And turns out this is a partial order on equivalence class of diagrams. I haven't, yeah, so, and it's not reflexive. And it's also anti-symmetric. Yes, which is what I'll get to. Yes, there has to be, yeah. Those are going to be the obstructions. They're going to be area relations. Okay, so can we find obstructions to the existence of such undercutting? And yes, we can find some, and they're going to come in terms of some areas. Okay. So let me try to describe what sort of my main theorem is. Okay, so the question is, we have two diagrams, D1 and D2, and can D1 undercut D2, right? Okay, so first what we want to do is find a big disk. Okay, so this is like some game, you're in a board game party now. So you have to find a big disk. So what is a big disk? So there's corresponding things when the pictures flip, but let's just do, so you want a disk in D2, so the upper diagram, okay, with all positive corners. Okay. A is aligned. That's a little like tricky definition, which we'll get to later. Ignore that for now. Everything I draw will have that. And the second one is also, so this is related to treating bubbling, the other condition. So the only thing I want you to concentrate now is you want something in the upper diagram with all positive corners. Okay. And that's a big disk. Yeah. Okay. So now once you find a big disk, you want to find a little disk to that big disk. So the pink thing, A3, is big here. And we want to find something little to it. Okay, what can it be? It can be something in the bottom diagram with all positive corners, or it's something in the top diagram where only common corners with A3 are positive. Everything else is negative. Okay. So you have A2 has one corner sort of common with this corner is common, and there it's positive, and this one is negative. Yeah, so that's allowed. Or these bottom disks where both are positive is also okay. Okay, so these are all candidates for little disks to A3. It has to be all positive. Yeah, so if you have something with a negative, that gets thrown out. Okay. Okay, so just some sort of sign conditions. Great. So then the theorem is if D1 undercuts D2, and if there is a big disk, then there must be a little disk with area smaller than the big one. Okay. Seems sort of vague with that picture, but it becomes much stronger later. And equality can hold only when you have one of these Lagrangian Cobordisms. Okay, so some like sort of trivial known cases, but otherwise it has to be strictly less than. Okay, questions? Yeah, A1, A2, A3 are in D2. B, oh, some labeling went away. Okay, sorry. B is in D1. Yeah, I should write that. Thank you. So this is D2, D1. No, just this one is big, just the pink part. And each of the yellow parts are little. Okay. Now you can do everything if like your big disk was in the bottom D1, you would replace all the positives with negatives and it would work. But let's not think about it. Okay. So here I've written down a definition of big disk when its boundary is in the like top diagram. If you wanted one big disk lying in the bottom diagram, you just replace all the positives with negatives. And yeah, just swap. Okay, but what is this bias? It's sort of complicated looking. So these are the same examples I showed in my 15-minute talk, if you were there. So if you have this sort of figure 8 sort of knot projection and plus signs, then it has to be growing as you go upwards. And if it's minus signs, it has to be shrinking. And you can get that. So in this picture, the pink, in all of these pictures, the pink ones are big disks, and the yellow ones are the little disks. And sort of the only candidate, because we took this to be exact, this A and the thing next to it has the same area. So both the little disks have the same area. So you get that. So these, for this one, it was proved by Savlov and Traynor using generating functions. I'll come to that in a bit in a 2008 paper. Did you do something? Can you sign in again? Okay, sorry people on Zoom.
Like our technical help here.
Yeah.
Oh,
Yeah, sorry about that. I guess I can keep talking. So this sort of results.
doesn't hear me.
No, they hear me from here, right?
No, the audio is going through there.
Oh, do Zoom people hear me? No.
Yes.
Oh, they do.
Really?
Yeah. Okay. Okay. So keep talking without visuals for a bit. So these things were like the figure 8 ones that you just saw, or you see now, were in a Savla-Freina paper from 2008, where they used generating functions. I'll talk about why why this is sort of more general in a bit. And then that picture I was showing you, if you assume some things about A1, A2, and A3, you can say that A3 has to be bigger than B. Yeah. But then we also get the same sort of growing and shrinking conditions for these trefoils, even though these are not exact Lagrangians. And we don't know anything about generating functions if you give me this. Even the exact trefoil, you can't do with generating functions, I think. But you get, so this is an exact case where you have like this thing has to be smaller than this. So in like examples, you get a lot of actual things. Okay, questions? Okay. So now I'm going to tell you how to prove some of these things. Okay, to the main sort of tool we're going to use. So the original Lagrangians we were looking at were embedded, and there weren't really, I mean, there were some holomorphic disks perhaps, but not very obvious ones. I want some more obvious ones. So I'm going to define the sort of immersed Lagrangian, but the immersion, like the double points, only happen at the boundary. So this looks like the same picture, but over here, you have a double point because I've joined them. So all the double points are like on the boundary. If you throw out the boundary, it's embedded. Yeah. And the boundaries lie in copies of R2. They have no height. So they're sort of flat. Yeah. Like previously we had knots. So they were objects in R3. Now those knots have height 0. So they're like immersed knots. And we want to keep track of these crossings still, even though it's like the boundary is sticking. So there's no like jumping down or up if you're moving along that curve, but just like one little bit under it, you can show that there's some sort of standard thing. And like just under it, you'll have an actual knot, which is like embedded. And for that, these signs that I defined before make sense. So for a Lagrangian tangle, the signs for the boundary are going to come from just the signs just below or just above it. Yeah. And the areas are whatever areas that curve bounds in R2. Like we actually have a legit curve in R2, right? The boundaries. And these are related to our Lagrangian Cobordisms because we can stick on some sort of small Lagrangian collars and go between, like we can, given a Lagrangian Cobordism, I stick on these collars which close up those gaps and I get a Lagrangian tangle. And I can make these as small, sort of as small as I want in height, which lets me like assume that sort of the areas don't change. Okay. Yeah, so this is an immersed object. Okay, let's talk a little bit about Lagrangian collars. So suppose you want to construct such a Lagrangian collar. It turns out that there's like a sort of easy relation. So suppose you want a function, so you want a collar, so it looks like S1 cross some interval, and you're putting it inside R4, and there's a map. So the first Z is two-dimensional. Yeah. And then it's Lagrangian if it satisfies some sort of PDE, okay, which is actually gives you a lot of freedom. So one thing to notice is suppose you start with some Z in S1, just some immersion of Z of S1 and R2, and you take a Hamiltonian on R2, yeah, and you're using the flow of this Hamiltonian on Z, and you put this height function as exactly that Hamiltonian, this thing is going to satisfy that relation. So so you can construct these, and you have a lot of control over this Hamiltonian. You can sort of decide your heights. I'm lying a little bit, but not too much. And if you started with some original height function, you could add it, and then you can like stick things on. Yeah. And one thing I noticed sort of recently is this doesn't have too much of a condition on the t derivative, right? So I can sort of vary the heights, like I have a lot of freedom. Okay, so you can play around with these sort of slices coming in families and construct a lot of Lagrangian collars to do, Yasha says whatever I want, but yeah. Okay, so these Lagrangian tangles, I can get them from cobordisms. Okay, but why am I defining this object? There's so much people already do with cobordisms. So I was saying Sabloff and Trainer developed these generating functions and some capacities from them, did like very complicated looking Morse theory, and they got a lot of good obstructions. And you were very happy. I was. But a problem is that generating functions don't always exist, or we don't know whether they exist or not sometimes. What is the generating function? So you want to write your Lagrangian as some sort of graphical object for a function from, like your Lagrangian lies in T star M in this case. But you take a function from M cross Rn. So it's a function on a slightly bigger space, and you're like doing a reduction and you get a Lagrangian. So this, then you can do the like functions floating around and you can do Morse theory on them. And if we have an unknotted planar Lagrangian, so unknotted means it's a giant Lagrangian, you want it to be isotopic to the standard, like the zero section. So I'm working with R4, which is T star R2. So you want something isotopic to R2. And like flat at infinity means outside some compact set, you legit want it to be the zero section. Okay, so this means that we can't have this sort of trefoils. So what happens is there's a number called the Reed, which is the number of positive crossings minus the number of negative crossings. And you can show that if it's a slice of one of these good Lagrangians, you can't do it unless the Reed is like plus or minus 1. So these pictures get ruled out. Like we just don't know how to start with them, with this theory. Okay, that's one thing. But then like I was like, oh, I want holomorphic curves. There's a lot of, oh yeah, I wanted to say that like because I have to bother about things like flat at infinity and stuff, it sort of feels like I have to know something about the global structure of L. I can't be like, I'm going to look only between those two slices, which could be difficult. Okay, but what about Legendrian stuff? Like people have done a lot of things with Legendrians. So in that case, you would be considering holomorphic curves in a symplectization. So R3 has a standard contact structure, and the symplectic form I'm taking is symplectomorphic to its symplectization. There's some factor of e to the power t sort of thing missing. And then you take holomorphic curves, which are asymptotic to Rabe chords, and they give you a lot of things, a lot of people with great looking theorems. But there are a lot more diagrams than Lagrangian knot diagrams, okay? So for example, this one doesn't have a Lagrangian lift, like respecting the sign. And that's just because your height has to be a function of the area. So if I don't demand that it's Lagrangian, I can go wild with what pictures I draw, what signs I put, what areas I put. These are like much less wild than that. And like if I try to do the same thing, like, okay, they're like, okay, I don't get Lagrangians, but what is the problem? Sort of these holomorphic curves won't have good behavior. So at like finite height, they'll shrink to a point like this and have some singularities. And that's not great. Okay. But so my Lagrangian tangles have boundaries sitting in copies of R2. R2, so if I look at R4 as C cross C, I should write that somewhere. Then these R2s are like standard complex planes, right? And any disk that you can see, and we've been like coloring all this time, all of those are holomorphic disks because uniformization. So then we can ask, okay, what happens if we want take one of these and let them move in R4? So they start in R2 and then we're like letting them move. Yeah. So we're setting some moduli spaces. Okay, I'm looking at unparameterized disks with corners, and the corners are at double points of the Lagrangian tangle, sort of standard things, right? And standard sort of quotienting. And this M bar will allow like nodal such objects, also sort of standard things we do. Okay, so these are the holomorphic curve moduli spaces I'll be studying. Yeah, some historical context. Okay. They can, yeah. They need not be. So the corners need to be at the, I want the corners, like the things at the ends, to be at the double points, but in between they, I don't have control, but we can show some good things about it. We'll get there. Okay. Okay. So this is like work in my thesis. I should have said that before. Okay, so then I come up with sort of complete description, maybe, I don't know, like complete enough for me to get those obstructions. Yeah. Okay, so we're going to make more definitions. Suppose we have a Lagrangian tangle. We call a holomorphic disk horizontal if it's one of these disks sitting at the boundary. Yeah, the ones we can see and have knowledge about. So the idea is we only have knowledge about the diagrams of the boundaries. So we only have knowledge about these horizontal disks that we're starting with, or like ending with. Everything needs to come in terms of these horizontal disks. So they are these like pink things, or any of these. Okay, so first lemma is if we have a horizontal disk with boundary on the positive boundary of a Lagrangian tangle, and it has all positive corners, so those big disks, or if it's in a negative boundary and has all negative corners, then the expected dimension of the moduli space is 1. Okay, so if you've been doing any flow homology, you're like, yes, 1-dimensional, that's what we want. Okay. Okay, so those big disks, the deformation spaces come in 1-dimensional manifolds, but we'll get to that. Okay. Yeah, note that this is the space of variations in R4. In R2, these are rigid. Okay, so the next thing is these horizontal disks are boundary points. Okay, what do I mean by that? They have sort of normal bundle Maslov index is 0. which means they divide this sort of, so suppose this bottom part is your L and you extend it a little bit. You can do that by adding collars or something. And you start with this U in the middle. All the disks in its deformation space will either be on top of it or under it. They don't like intersect it. Yeah. And that means we have some sort of moduli space like this with our favorite point U sitting in the middle with everything on either side. So we can chop, when we impose the condition that we're looking at y2 less than equal to b, we're sort of chopping this off very nicely and getting an endpoint of a moduli space. Yeah. Okay. These are compact. That had to be coming, right? So the compactness, you can use sort of usual immersed Lagrangian compactness, but like, okay, R4 is not compact, but my boundary conditions are compact, the Lagrangian tangle L. So I can restrict all my attention in some box. And then using the fact that this is this sort of flatness that lies in R2, these disks don't like escape in any direction really. So you can say that it's not getting to the bound anywhere near the boundaries of this box. And so everything is very controlled, and standard compactness gives you compactness. And there's automatic transversality because I'm working in dimension 4. So there was results by Hofer, I mean, they've written it down very nicely, Hofer, Lizan, Sikora. And by making changes to the argument to account for the corners, it works. And so now we have compact one-dimensional manifolds, okay, which is great. Okay, and I have a compact one-dimensional manifold with a horizontal big disk giving me a boundary point, okay? So there has to be other boundary points, yeah? And finding these should tell me something, okay? So this is quest, okay? That's the octopus giving me the quest. Okay. Huh. How do I make this go away? Minimize. Nice. Okay. Okay, so to describe these other boundary points, I need to make some more definitions. Yeah. So we had signs for these horizontal disks, right? Because we had signs for the diagrams and the horizontal disk was sitting on the diagram. So they have a plus or minus that come for free. But we want to extend this to give us more information. So near a double point of the Lagrangian tangle, you have exactly 2 leaves because I said only like transverse self-intersections are allowed. And like one of these leaves has higher x2 values and the other one has lower ones, like very close by. So using the x2 values, I can say you have a higher leaf and a lower leaf. And for any holomorphic curve, so it doesn't have to lie in there, it can come like from the bottom. But if it touches one of these double points, I can, the boundary gets an orientation because it's holomorphic. And I can ask whether it goes from the higher to the lower or the lower to the higher. Yeah. And then I'll assign the same signs as we had before. So I'm extending this definition of sign to any of holomorphic curves that appear for me. Yeah. Yes. Yes. So the sign is at a corner. So sign of U at corner Q. Yeah. Both are important. Yeah. Okay. And then we have this lemma, which should not look too surprising. So if you have like a stable disk, meaning like a broken one with a node, and that node is like a corner. So it does come at one of these double points. So like Barsh said, it can come in the middle and then this is not there. But if it comes at a double point, then the signs have to be opposite. So whenever this makes sense, you have to have opposite signs. Okay. And for this, so if you look at Floer homology and you have sort of a strip going from some point X to Y, comes with the direction, right? And when it breaks, you can have x to z and z to y. You can't have the other way around. Yeah, so this is the same thing, but these are not strips, but you can define it like this, but it's the same idea. Okay, so you need to have opposite signs whenever these breakings happen. And the other cool things about signs is that suppose you have a non-horizontal disk, right? So horizontal disks we saw can have any signs, right? Plus, minus, there were lots of options. But if you have a not horizontal disk, at the top boundary, it has to always have positive signs. And at the bottom boundary, it always has negative signs. I'll tell you why, but they have to look like these. They can have more corners, but. Okay, I'm going to tell you why. So suppose we have this double point at the top boundary. Okay, we can take some sort of local model. So we take two projections, one to the x1, y1 plane, and the other to the x2, y2 plane. Okay, both of these are holomorphic. And the Lagrangian does something here. Looks like sort of two straight lines, can be curvy, like don't care. But this one, everything, so this is my y2 equal to b line. So everything is under it. So it looks like sort of two lines like this. Yeah. And this one is going to be the higher leaf because it has higher x2 values. And this one is the lower leaf. Yeah. And now suppose we have a holomorphic disk, which is going through that point Q. Then you can take its projection to this picture, right? And that's going to still be holomorphic because that projection is holomorphic. Okay. And because U was not horizontal, this projection is not constant. Okay. So then you stare at this picture, and what's the only non-constant disk you can draw with these conditions? It's that pink one. Yeah. Because the boundary has to be on these Lagrangian projections. And then because there's only one complex orientation, it has to go like this. So it goes from higher to lower. So the sign is always going to be positive. And on the negative boundary, it's very similar. Okay, so this is like very, this gives you a lot of things. Okay, yeah. Questions? Okay, so now we're going to start putting things together. But before that, let's talk about this aligned business and also talk about breaking in the interior of the Lagrangian. Okay, so my claim is if U is aligned, whatever that means, nodal disk with smooth nodes, so nodes inside the interior of the tangle come in pairs. And whenever things come in pairs, I can throw them out. Like my quest is still open because of I need even number of boundary points. Okay. So I mean by smooth node is a node away from this, so something like that. And these will be smooth points for both of these disks. You can show that like the nodes are as nice as the Lagrangian is. Okay. So what is this aligned condition? So if I have a disk with corners, it has its boundary is like sort of broken into many bits. Yeah. And each of the bits, like each of the smooth bits, gets two orientations. Okay. One comes from the orientation of the Lagrangian. So I'm taking oriental Lagrangian. Yeah. And the other one comes from the orientation of the holomorphic disk. And if they match, we say plus. If they don't match, we say minus. But we want to say they're aligned if all the boundary arcs have the same sign. So this one is not aligned because that's the orientation on the Lagrangian, but the holomorphic orientation is this way. But here everything's aligned in this one. Okay, but all this is it's some orientation condition on the boundaries, which lets us say this thing that that smooth nodes come in pairs, by which I mean This is what I mean. So if you have one sort of u1, u2, dot, 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 un sitting inside m bar u, such that the common node between u1 and u2, this one is in the interior, so it's smooth, then there'll be one more, like you can pair them off, okay? They'll always come in twos. Okay, so basically moral of the story is if I take my initial holomorphic disk to be nice enough, I can not care about these interior breakings. Okay, but then putting all of this together, we can show that these one-dimensional manifolds have to have even number of boundary points that look like one of these. So either it's just a horizontal disk, the ones we start with, yeah, or it's like a combination of horizontal and these not horizontal ones, but the not horizontal ones have very strict signed conditions on them, right? And the big disks were the ones that came on their own, the horizontal disks, and corresponding ones. So that one could break into this thing or this thing. So that will give you candidates for your little disks. And because areas are preserved in these moduli spaces, right? And holomorphic disks always have positive area. These yellow ones must have less area than those ones, except in some like cylinder cases. Okay, so just tracking, comparing all of these, like we have a lot of different things coming, but we look at only the horizontal disks that are appearing and comparing their areas give us those obstructions that we were looking at before. Oh, so suppose you start with this with minus things. And yeah, so in my definition of big disk, I said you can like replace all. So now this one is big, right? And it moves like that. And then it breaks into this. Yeah, yeah. Yeah, moduli space per big disk. And then that breaks into things. So I'm looking for candidates for breaking. Yeah, so let me, yeah, you can have anything you can imagine really. So that's when you get the same area, right? And then you'll have this disk is going like that. But then you'll have the same area. But for that same area to happen, you have like topological constraints. So then you know your Lagrangian looks like a sphere minus 2 points. And there's only those sort of 5 options where that can happen. Yeah, but that can happen. But you can also have, if you had something like this, even with stuff at the bottom, and this was your big disk. It moves like that. And so this is plus, but if this were minus, you could have this. And so then my broken disk would be this one plus this thing. Wait, that's too much genus. I messed something up. Oh, sorry. It'd be like this. Yeah. So it can fold, but still break. Yeah. So a lot of things can still happen. So you don't get like super nice conditions unless you have very few disks. Which is why like one of the results I had was like, you assume a bunch of things are bigger, and then the only left like small thing has to be smaller. Or it's like one of like the minimum of a bunch of things will be smaller than your big disk because you have multiple candidates for little disks often. Yeah. More questions about this?
You can't use this to code other things, like stuff the little disk and code the big disk.
No, so the little disks don't move, right? So the big disks have like dimension 1, like the moduli space, and they break into these things. So the dimension's falling, so they don't move. But because you said that, you can have, suppose you start with something like this. There are examples where the candidate of the breaking is like that. So the 3 of these make my little disks. So the dimension can fall, like the expected dimension can fall much more than 1. And you get these like not, so what happened is we're not looking at a generic situation. I forced my boundary to be in R2 and I fixed my holomorphic structure. So you can get things like this. Yeah, so the dimension can fall a lot, but it's at least falling a little bit. So they're like, they're rigid in the 4 dimensions also. Yeah.
Give partial orders, right? Of the, you have, for instance, 2 cobordisms. You concatenate them somehow.
Yeah.
Maybe that's not a local tangles, etc. But
You can, yeah, so you can concatenate the cobordisms by like adjusting a little bit so you have the same knot and then sticking them smoothly.
so for instance, you have to start with a big disk on the top.
Yeah.
Go to middle disk with smaller area. I'm just trying to fix it into
Okay, so I think, okay, let's just do this. So suppose you have a big disk, suppose you have this one, right? With the pluses, which is like growing. Yeah. So this A, so A has to be bigger than B, right? And now I have one more where this is B. And if I have something here, this will be B greater than C. Okay, but now what happened was, so for this one, this was big, right? And this was its little thing. Okay, so which means, so this can't move up. This B cannot go up. Okay, but in the bottom picture, this is in fact big, which just means it can go down. So there's a directionality in which it can go. So all of these little disks cannot move in the direction I've given it a Lagrangian, but in the other direction they can move. So if I make the standard extension, they'll start going down. So does that answer your question? Okay. That was mostly all I had to say. I have some future ideas. Like usually there's some algebraic structures where you can write things down nicely and compute things. I haven't found one yet. I'm talking to Josh. So all of this was like breaking. I didn't talk about gluing. Usually there's gluing somewhere when you talk about moduli spaces. And because of Barish's question, we saw that there were like these negative dimensional moduli space disappearing. But I'm in progress of writing it down. Some obstruction bundle gluing techniques can glue them because they're nice, even though they're in negative dimension moduli spaces. And then there are other algebraic structures and capacities that people have already developed. Hopefully we can find some connections. And I guess another question I had is like, so I had something that said, if this knot is sitting on top of that knot, it has to like grow. Okay, but then I can ask, like, if I'm allowed to just change the areas as I want, can I always build Lagrangians, or like what are the obstructions there? Like more constructive sort of questions can be asked. And I'm not sure yet. Yeah, thank you.
So is the algebraic structure, I mean, it's like the kind of thing that you're gonna try to look for something because these things kind of look like Lagrangian Cobordisms in like the Veron-Cornea sense or something like that, or maybe like the Legendrian Cobordism. Like there's sort of this approach to like Legendrians in like R2 cross in like R5 as like cobordisms between Legendrians and R3 or something like that. So I don't know if that kind of
yeah, so yeah, the Veron-Cornea thing is not exactly what this is. I agree it's close. I forgot exactly why it's not. There's it's slightly different. But the thing I can say is what I find disturbing is that we're sort of looking at like if you look at the indices, like the dimensions of things, usually when you look at like things in the cobordism level have are appearing in a moduli space that's different from those appearing on the flat level. But here that's not true, right? So it's something that's starting on the flat level and then moving down. So and somehow that's been, so there are like some sort of zero differentials or zero cobordism maps there, and it's been confusing. But that is sort of what I was thinking, but we're not sure it's.
Wait, so you're saying that you're just saying that the virtual dimension of the disks in the sorry, can you say what you were saying again?
Yeah, so yeah, let's just do this thing. So the virtual dimension is 1 for this. And this is 0 and 0. Right.
Yes.
Usually you would have something, if I understand correctly, like either like if you're looking at Floer homology stuff, you have like 0, 0, and another set of 0, 0. That's not what's happening here. And in the cobordism story, I guess you look at, so you usually there's something like cobordism map composed with derivative, something like that.
Yeah.
Something like this.
Yeah.
And then
maybe on the notes again.
Sorry. Yeah. And this is 0, but that's not the case. Like this, you would imagine that this is your Bordism map. I don't know. Numbers don't seem to match up if I try pushing this. Or you could, or have like 0 and 1, but even that is not. Yeah.
Okay.
Or 0 and 0 even, but then on this side we have 1 and what? Okay. So okay, maybe it's better, like there's some subtraction going on, like there's a -1 or something, but even then I'm not sure. Maybe by next year I'll have something to say.